in Lab 2 for Physics 2212. The purpose of this lab is to take a deeper look at how neutral objects can become polarized and interact electrically with other charged objects. We built off of concepts from Lab 1, but this time we focus more closely on the modeling and what is happening at the particle level within the tape. And the main physical principle governing this whole experiment is Coulomb's law, which describes how charged particles exert forces on one another. Our goal was to connect physical observations with a digital model and compare both to theoretical predictions. At the core of this lab is Coulomb's law. Coulomb's law states that the electric forces between two charges depends on the magnitude of the charges and the distance between them. The equation is F equals K, which is a constant, times charge 1 times charge 2, divided by the distance between the two squared. This tells us two important things, which is first, the force increases if the charges increase, and second, the force decreases rapidly as the distance between the charges increases, because it follows an inverse square relationship. In our experiment, we observed both repulsive and attractive interactions, depending on how the tapes were charged. Even though the tape itself is neutral overall, the distribution of charge within it changes due to polarization, which leads to the measurable forces. In our model, the bottom tape represents the surroundings, top tape represents the system that we're analyzing. The tape length was about 0.15 meters and the width was about 0.02 meters, and the mass was about 1.02 times 10 to the 4th kilograms, or negative 4th kilograms. Instead of treating the tape as a single charge, we tried to model it as many interacting particles. This allowed us to analyze how each small charge element experiences a slightly different electric force depending on its distance from the other tape. One important thing to note is that this was not a perfectly isolated system, so surrounding environment and other nearby charges could slightly influence results, which is realistic in most physical experiments, of course. Now, here is some of our code in the computational model. Using the experimental setup and modeling the forces between charge distributions, we solve for the effective charge on the tape. From our calculations, we find that's about 1.7 times 10 to the negative 8th, as you can see here with our model and results. This value represents the magnitude of charge necessary to produce the observed forces consistent with Coulomb's law. The digital model also helps visualize how forces vary along the length of the tape. Charges closer together will experience stronger forces, while those farther apart will experience weaker forces. This variation matches exactly what Coulomb's law predicts because of the 1 over r squared relationship. Now, for some possible questions. The lab raises some interesting theoretical questions, such as first, what if we treated the tapes as point charges instead of distributed charges? Doing this would simplify the math, but it would ignore how force varies across the tape's length. Our model shows that distributed charge gives a more realistic result. And second, what if the forces were attractive instead of repulsive? The mathematical structure of Coulomb's law would remain about the same, but the direction of force would probably reverse. The magnitude would still depend on the charge size and distance. And third, what if we use different material instead of tape? Different materials have different tendencies to gain or lose electrons. This would change how much the charge builds up and therefore change the resulting force. In conclusion, this lab demonstrates the interaction between charged particles in the tape and can be directly observed and accurately modeled. We saw physical evidence of electric forces in person through attraction and repulsion, and we reinforced these observations with digital simulations that model particle-level interactions. Our results align closely with Coulomb's law predictions, confirming that electric force depends on both charge, magnitude, and distance squared. Most importantly, this lab helps bridge the gap between theoretical equations and real-world behavior. Instead of just working with formulas, we're able to see how it works at the microscopic level in terms of interacting with each other, and how this produces measurable macroscopic forces. Thank you.